guess it's focused on. Okay. Very good. The lights are two-stage here or not, they're all on one switch.
No, it's flat.
Just that side. Oh, the switches on the other side?
No, I mean, it's flat light.
Is this control? Let's see here. There's only screen control, projector controls, no light control. All right. Anyway, it's one of the older rooms, I guess. It's not. I don't want to turn off the main lights and you guys sleep on me. All right. About the project. Let's talk about the project a little bit first. In the project, we're talking about designing a lambda by 4 waveguide section that matches two other lines, right? So we have a waveguide section, let's call it A, another wave section, call it B, and this one here is air filled, and this one here is directly filled. Okay? Obviously, the impedances are mismatched. Right? So what do? We put in between another section, call it MS matching section. All right? And we're going to fill it with dielectric. Let's call this here epsilon R matching section. Okay? And obviously the length of the matching section. From what we know from transmission line theory, which applies here very well because we're just simply talking about impedance matches here. The input impedance here is related to the parameters here as well as the termination impedance here. So we can work this one out. ZL here, ZN, if you wish to call it eta N, and eta L, because we're working here with etas instead of z's. Eta is what? Is the ratio between E and H, while Z is the ratio between V and I. We don't have voltage and currents here. We have fields, so we're working with etas. Eta is the intrinsic impedance of the waveguide. All right? Now, the same relationship that we've seen before, eta N is equal to eta, call this one here eta naught, times, you have eta L, I believe it's eta naught plus eta L, I have to put a tangent of gamma L, divided by eta L. I may have it backwards. You guys can confirm that later on. It's either that or eta L times plus eta naught that. It could be backwards here, right? Is it backwards?
Yes.
You think so? You all think so? All right. Like I said, I don't try to memorize equations, I usually derive them. So, if you have memory better than mine, then this is what you have. So, that works out if we work lossless, J beta, and a J beta here means we can convert this to J tangent of beta L. Right? If we assume that the losses are negligible, so we can work this one out. And if L is lambda by 4, then beta L, all these are guide, beta G and lambda G, because we're working with waveguides here. and eta guide. All these are guides again. Eta G, 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 G. All these are G's, okay? Because we know it's not just mu and epsilon. The mu and epsilon and the geometry and the mode, which mode we are working in. So if you wish to be more complete, you should write M and N for that particular mode, all right? If you want to be precise in all your expressions, which I try to do in my notes, I write all the subscripts. Obviously, when we carry on the board here, we want to be kind of brief, so we drop some subscripts sometimes. So if you want to be precise again, that's Latin guide MN. For that particular modes, MN. Gamma guide MN. Okay? So all these now, I think, did I miss any? Anyway. So in this case here, beta L becomes 2 pi over lambda guide. This quantity here now becomes 2 pi over lambda guide Mn times lambda guide Mn over 4, which becomes pi over 2. When you have pi over 2 here, that means the tangent pi over 2 blows up to infinity. That means you ignore this part and you ignore that part, you end up with eta naught guide Mn squared divided by eta guide load Mn. Right? We've seen that before. That's for the lambda by 4 line. So if I use a lambda by 4 line, I can use it as a transformer between two different impedances. So what I need to do for this one here is make L of the matching section is equal to lambda guide Mn over 4. And then choose your eta naught of the matching section at the MNN mode, right, of the guide with all the subscripts is equal to the square root of the two etas. Eta desired to be eta input times eta of the load, right? You choose it to be the geometric mean between the two impedances, and if you do that, then we have the matching satisfied. Sounds good? In transmission lines, that would be an easy thing, and you simply multiply 25 ohms by 75 ohms under the square root is equal to, and you get an answer, and we're done. Well, here the story is different because there are modes, and we have to watch out for cutoff and propagation. Okay? Your lambda guide changes frequency. Here, right, you have one frequency. In the other case, you have a band. You are operating in a band. So the two equations are not exactly independent. And here, the equations were independent. These are related to each other because they both depend on Mn. So we'll go see the first section of the guide, guide A, and we find that section operates between these two frequencies, FC1 and FC2, whatever they are. The first cutoff and the second cutoff. Right? You look at the second guide, and it will have its own operating frequency. Right? Let's do that in different color. Red. Right, guide B, that was guide A. If you look at guide B, I'm just going to assume different frequencies, like here and there. Right? Could be the other way around, you know. I'm not saying this particular case, you know, it could be the other way around, could be below and above. So that's FC1 here, FC2 of guide B, that's guide B. And that's guide A. In this case here, that's your TE10. That's the same TE10. You want to make sure it's the same mode, because your field in the TE10 is going to be going this way, that's your electric field, right? And when it propagates, I don't want it to go eventually to a field that will have a TM, for example, all right? Because it's not going to be a continuous situation. Your field is not going to be the same. So if your field is going this way, you want it to continue to be the TE10 mode. If you put it in a guide that works with the TE20, you know that the 20 mode does that, and the 10 does that. Obviously, this field is going to get killed as soon as it hits the other guide, right? And you are going to lose the TE10, and you're going to get the TE20 mode, right? So usually, unless you do that on purpose, usually you want to propagate in the same mode. So that's the same mode. That's your TE10 mode right there, this region here. And the TE10 mode for that is this region there. So obviously, your mode of common operation, your region of common operation is this region here. So that is your region of common operation between the two guides. You don't want to go that far, this guide will be cut off. You don't want to go that far, this guide is multimodal. Right? Now, add to that, you're going to put a matching section. Right? And assume that you already know epsilon for the matching section. Assume, okay? Which we don't yet. So that is eventually going to do its own thing. It will have its own cutoff. It will have its own 10 mode right there. Obviously, we limited ourselves now to even a smaller mode. So that's now the common region of operating frequency between all three guides. And logically, your carrier frequency, if you are sending a signal with carriers, your carrier frequency has to be somewhere in the middle of that. So you want to call this here your operating frequency. So before you do the design, you don't know your operating frequency because you don't know what you have here, right? So there may be some trial and error, some assumptions that you verify, things of that nature, right? It's not going to be like a one solution kind of thing. It's not a bunch of equations that you put into a computer program and expect an answer, okay? So initially, you don't know this one here. So initially, you're working with this region here. So initially, you may be assuming that you are operating here, and you are going to design your matching section for that particular frequency. You need to know the frequency to be able to work with this, because none of these equations will work unless you have a frequency. So maybe you can work these equations in a tabulation, if you like. There are two possibilities here. Is one to assume a frequency and work with, but that frequency may end up to be outside your end band. The wiser thing to do is obviously to assume all the frequencies here first. So make a tabulation, write your code, so you can produce from, we'll call this one here FC1AB and FC2AB, which is the cutoff frequency of the common A and B. So you start with FC1AB, and you increment here all the way to FC2AB. You write in the equations, and you find out for each one of these frequencies, all right? You want to work out this relationship here. Find your impedance of the section. And find the epsilon for your matching section. Find the wavelength for your matching section. So you have a bunch of possibilities here. Then for each epsilon, you want to find out your cutoff frequencies. So for each one of these epsilons, you will have FC1 and FC2 of the matching section. I'll do it this way. For each epsilon, you have FC1 of the matching section and FC2 of the matching section. So you're going to see this thing here slides, right? Depending on which frequency you're working with. And you're going to optimize. You're going to choose your best epsilon among all of these, and based on that, you go back and design. You may not understand everything I'm saying, you may disagree with some of my approaches, but the thing is, you know that there is an issue that needs to be looked at, okay? It's not a closed solution kind of a problem, right? I'm suggesting this. That's not the only way you can do it. Okay? That's what I'm saying. But obviously everything else is valid. It's the only part here that I'm proposing as an approach. But I'm sure that there are other approaches that you can think of. Questions? Another alternative, which I mentioned earlier, which is iterative. You start with something and see if it works, or it guides you through, and then you can choose something else. Now, usually, as we saw earlier, let me put this also in consideration, because designers put in mind all these kind of things. Now, one thing that you notice here is we kept the dimensions the same. That's for mechanical convenience. Sometimes, we design guides to taper to different kind of dimensions, right? You may have a situation where you design guides this way, okay? These are also possible. Two different guides, different cutoff frequencies, and your matching section will be tapered. Now, this particular case here, they are all the same dimension and different filling, okay? Just to be aware of that other possibility here. Now, what I wanted to add is the attenuation. If you remember, if this is FC1 and FC2, the E10 mode, the attenuation almost goes to infinity here, dips around 1.5 and grows again. So as you can see, things are not exactly symmetrical in terms of the bandwidth, right? So usually if you want to do this kind of a situation with attenuation, with losses, right, you end up with some different margins on the sides. You have a bigger margin here. You don't want to come too close here if you want to maintain a decent attenuation. So working with the middle frequency is, call it the first iteration. Designers obviously try to offset things to use the lower attenuation band or the lower attenuation frequency range of the guide, right? You don't want to really become in the middle. You want to be a little bit to the right. So your center frequency typically moves to the right a little bit. So keep all that in mind when you design. I know we are not working, we don't have equation, attenuation information to work with, but like I said, just be aware of all that. Now, last lecture, any questions on this before I move on? Do you have any questions on the homework? Is the homework all right? Okay. When is it due?
Next class.
Wednesday?
Yeah.
All right. Okay, last lecture we did the cylindrical guides, or the circular guides. circular or cylindrical. You know the word cylindrical applies to rectangular guides as well. Most of us don't realize or don't think about it that deeply, that a cylinder is an upright shape, irrespective of the cross-section. Right? So you can have a circular cylinder, you can have a rectangular cross-section for a cylinder. That's linguistically, but we usually don't use it that way. So we prefer to call it circular guides and rectangular guides rather than cylindrical guides. But we get loose with the language many times, so you can let one go by. So the next thing in circular guides really is to talk about, if you want to go further in circular guides, you want to talk about two things. One of them is a coaxial line, and study the higher order modes that happen there, because we never did. All right? And the second thing that typically goes after that is the directed guides, which is a fiber optic. Right? But I'm not going to do those two in the lecture. I'm going to send you something to read about the coaxial guides. The math gets involved, right? It gets too complicated. And I'll send you another one on the fiber, so you can read and look at the nature of math involved and the kind of things that we can conclude. And if there is time at the end of the class, the end of the course, we can revisit some of those. And those could be, by the way, subjects for the second project. The second project will be a research topic that you choose and write something on. What you would do is write me a proposal on what you want to do, and we approve the proposal, and then you start working on that. Right? That's going to be the second project. So we jump to strip lines and microstrip and planar geometries. Right? Those of you in the lab already have built microstrip lines and did some measurements on them, and have seen some of the equations and used some of the tools. But we want to talk about them in the lecture here, because as you will see, the equations that we have are all sort of empirical. You know what empirical means? Empirical means, they came by experimental data that was eventually converted to some form of a matching equation or a fit equation that doesn't imply or represent the true mathematical feature. Right? The data may be of any complex equations, and you simplify it into a parabolic or a exponential, what have you. Any of these are called empirical expressions. Now, these pages are Xerox from an earlier copy of Posar, and so they are also in the newer thing. The thing is, the font in the earlier copies were much more bigger and clearer to read. The recent edition have smaller font and kind of hard to copy things from. So you have that material there, and you can always look on those kind of things online. Lots of references on planar geometry, papers and presentations on the web, so you can look at those as well. The advantage of the planar geometry is, construction. They are not mechanical anymore. Right? If you notice, the coaxial line is mechanically constructed, that is, and fiber is mechanical. Waveguides are mechanically constructed. Well, these planar things are not exactly mechanical, because you can do them in laboratories by thin film and thick film and microelectronic things. But obviously, you can't make long distances of those, right? So these kind of things are suitable for integrated circuit applications, microelectronics and the likes. Printed circuit boards, microelectronic chips, nanoelectronics, all these kind of things use these kind of geometries. You can't build a coaxial in thin film or thick film or any of these technologies. So the technology here is basically the planar technologies, printed circuit boards, and the likes. Now, the printed circuit board, the typical one that you see in if you open your PC or open your camera or whatever, any electronic device that you have, there's always a printed circuit board made either thick and flat or thin and ribbon kind of thing that flexes, all these kind of things, and have these conducting lines that go in there with the frequencies that we use in these kind of things that reach in the upper megahertz and the gigahertz. You know, we know that these are actually transmission line theory kind of candidates. You know, we can't just analyze them by ignoring these lines and say, you know, the voltage at the beginning is the same as the voltage at the end. These are transmission lines because they are bigger than negligible compared to the wavelength. So they need to be analyzed in that context. The closest one to approximate to a coaxial line is this one here, which is called the strip line. The strip line is kind of a flat coaxial, if you wish. The center conductor becomes a thin strip. As you can see, we are showing it as width W. Typically, it has a thickness. Thickness is referred to as T. In the analysis, usually it gets neglected, but if you want to do a better analysis, you have to account for the thickness of that conductor, because that thickness not only controls the field distribution, but also controls the evaluation of the losses, because that thickness eventually controls the resistance of that strip. The center strip will have some resistance, and the thickness obviously will be compared to the skin depth, and all these kind of things complicate the analysis further and further. The outer shield, as you can see, is from the bottom, the top, and the sides. The side shield is the hardest to make in planar geometry. You know, usually we work with layer things. We layer things together. Going vertical is hard to achieve, right? So typically the vertical thing happens through what we call vias, all right? Going through the dielectric insulation between the conductor sheets with vertical holes and fill those with conductors. And those vias are going to be an array of those. You can make it as close as spaced as you like, but obviously their location determines the behavior of the whole circuit, because those vias are not going to be perfect, and they will cause issues. First of all, if you imagine that you have a ground plane here, and another layer here that you want to make ground, and eventually you're going to connect them with that, all right? Obviously, you know that there is some resistance everywhere in there. You know, these are not perfect conductors. And these vias are basically resistive as well as inductive. Right? So if you imagine your transmission line now, right? And this one here is grounded everywhere, but this one here is not grounded. The center conductor is right there. This one here doesn't connect to that. It connects to that through resistance and inductance. And they are placed every so often. So they obviously are going to cause problems. The point is, what I'm trying to get to is, you know, to do analytical development and write equations for these kind of things is near a nightmare, all right? So it's actually impossible. Now, what we do is typically we either, in the old days, obviously there was no computer simulation that can be trusted, so we're building those, different dimensions, different geometries, different material, and collecting data, measurements, and trying to fit those data to the pattern, right? So you try to get Z naught of this kind of thing versus everything you can think of. The width here W, the thickness T, the spacing D or H, typically it's called H, right? Or T equals B here. Anyway, B, let's use the same notation. The epsilon and the conductivity of the metal, sigma, you do all these kind of things. And you collect tons of data, and then you fit two curves. And obviously they are going to be parametric, because you have so many parameters changing. So, I don't have a picture of such curve, but they get too complicated. And basically, after all this effort here is done, you come up with some form, you use some optimization package, where you come up with an equation like this. For example, look at this one here, right? Z naught is equal to 30 pi by square root of epsilon r, and you have WE plus 0.441B. And the question is, look at the units here. The units are not right. You can't take an empirical equation and say, well, that doesn't work out. Where are the ohms? There's nothing ohms here. You have square root of epsilon r in the numerator, that's dimensionless. And you have B over W, that's dimensionless. Everything is dimensionless. So the right-hand side is actually a number that doesn't have a unit. Well, the left-hand side is ohms. Right? But that's how empirical equations work. Right? They don't necessarily work with units. So you put on the numbers on the right-hand side, and you get a characteristic impedance number on the left-hand side, and that's about it. And sometimes they give you different equations for different regions. Sometimes your equations don't quite match a particular trend. So you fit this to an exponential decay, and you fit this to a parabola, and you fit this to a linear part. So you may divide this into three regions and say, if I'm in this region, I'm exponential. If I'm here, I'm parabolic. If I'm there, I'm linear. This is how these kind of things work. So you can see if W over B, WE, see he used WE. WE is what we call effective width. Right? The effective width is equal to W over B minus, if the W over B is greater than that, it would be W over B itself. If it's greater than that, you correct it by that coefficient. Right? So you see all sorts of things of that nature. You look at alpha sub C here. Alpha, there are two types of alpha in this case here. Two types of attenuations. Attenuation because of the conductor, and attenuation because of the electric. And both of them have to be accounted for. And as you can see, there is a very complicated expression for alpha C, and there's no way you can think that this is derived somehow. Right? 2.7 times 10 to the minus 3. What's that? Where did this come from? It came from the curve fitting expression, and you have an A and B, and look at the A and B. Right? Again, more complicated expressions. Now, we take these kind of things for granted, and we just use them because people before us tried them and they work. Well, as it turned out that you have so many of those, and they are all different, right? And you open two different references and you see different expressions, and they all claim that mine works better than the other guys. Now, nowadays, we try to resort to numerical solutions to come up with those answers. And there are acknowledged packages, software packages, that have these kind of equations built in, all right? Based on computer simulation most of the time, very little on measurements, because even the measurements, there's always some question mark about how well was it measured and whether it was measured properly or not, and what's the accuracy of these equations, and how well was the fit, all these kind of things. So using packages like high frequency structure simulators, HFSS, which uses finite elements. There are many other packages that use finite difference in time domain, finite difference in the frequency domain, and method of moments, and some of these things that can give, they usually go for the S parameters. You give you the S parameters with structure, right? You give a structure like this one here with, even you can model all these various, whatever you can draw in AutoCAD, you can feed into these packages. And, you know, with as much detail as possible, and much information about the dielectric, as much information about the conductor, and you can get your numbers there. Now, we're not going to do this for every small project that we have. Usually that's done for things that deserve that much research. So we resort to something like PSpice. Remember PSpice or Spice? Spice does what? Spice had these built-in models, right, that were verified and authenticated, and you just pick them and throw them in a circuit, and you assemble your circuit. Here's your transistor, here's your resistor, here's your inductor, and you put them in. Well, there are similar things to that for high frequency. And there are several packages, right? One of the famous ones is the one that's done by Agilent, the Advanced Design System. That had many names in the past. I think it's called ADS now. And basically it has those built-in models for different things. So you can put in a strip line, right? And